snow metamorphism. So what I have here is the International Classification of Snow Crystals table, so the basic classification of the different snow grains and then their sub-classifications or shapes. And I like to think about snow metamorphism in terms of the types or habits of crystals, snow forms that are created. The previous discussion talked about dry snow metamorphism, so that's when you only have solid ice and gaseous vapor in equilibrium with each other, and you end up generating forms either of these high surface area kinetic types or these low surface area rounding types. This is in the colder months of the year. And then once liquid water is introduced into the system, now we have a three-phase equilibrium, and that drives slightly different processes, and we call that wet snow metamorphism, which is orange here. And then sometimes that's it. Sometimes that's all the categorization that's discussed or that is warranted. But often, because of the sort of uniqueness of the physical processes that occur, I like to break out melt-freeze crystallization as its own topic. And these are typically radiation-driven processes. They don't have to be, but they often are. And there's four subcategories generally. This is not hard and fast. Sometimes this is discussed as one single category, and sometimes it's discussed as multiple. It really depends on the types of physical processes that you're using to classify or differentiate the different processes that occur here. But there's two main takeaways for melt-freeze crystallization processes. One, it can occur in either wet or dry snowpacks, so meaning you can have either just a two-phase solid gas system, or you can have a three-phase solid liquid gas water system. And often the products of melt-freeze crystallization are kinetic persistent types that are high surface area grains because the processes are being driven rapidly far further from equilibrium, which in the end yields a less stable snow. First category we're going to talk about here is melt layer recrystallization, which often, I think by modern standards, goes by the term dry on wet faceting. And so in this case, what you have is a typical snowpack that's sub-zero, and then you have a distinct event where some thaw occurs because of warm surface area. You have some slush fall or rain on snow. And what that does is it creates a warm layer of wet snow on the top. Since you have liquid water, remember you're pinned on the phase diagram, the equilibrium phase diagram between liquid and solid. That means you're stuck at the melting point, which is 0 degrees in this case. So you're at 0 on a colder snowpack. And then you have a second event, which is new cold snow that is often below 10 C, could be as low as minus 20 C, that falls on the wet melt layer that's sitting at a warmer temp of 0. And so you get a latent heat transfer, and that freezes the ice as a crust layer. So depending on the thickness of that new snow layer, what you've essentially established is a temperature gradient because you have 0 degree snow right at the moment that it freezes, and then you have much colder dry snow on the surface. You can have fairly large or extreme temperature gradients that are established across the top layer of that new snow layer. In some cases, that temperature gradient can be anywhere from 100 to 300 degrees C per meter, so extreme gradients over a thin layer, which of course enters into this kinetic regime where you have very rapid growth of crystals, so dendritic crystal growth, which establishes these facets, and those facets are forming on top of that original wet snow layer that had formed into a crust. So what you have then is a hard crust layer and a soft, typically lower density faceted layer on the surface of the crust layer. And this is why this is called dry on wet faceting, because we had the dry layer on the wet snow layer, we had a freezing event because of latent heat transfer, and then we had this very large thermal gradient that's established in that top layer on top of the crust layer, which motivates rapid kinetic growth of these faceted forms. So here's a cross-section of a pit where we have a dry snow slab that, and then we have a thin faceted snow layer on top of a 4-inch thick melt freeze crust. So that faceted form is or was occurring on top of that melt freeze crust, which was our wet snow layer originally. So likely what happened here, so we had an original layer, we had a thawing event, and then we had cold, dry snow that fell on top, and then we formed this new faceted layer. The problem with this snowpack stratigraphy is it's a common avalanche failure layer, especially in warmer maritime snowpacks, where you have the propensity for 0 degrees wet snow layers, meaning you have sort of warmer coastal environment, and you can have rain that falls, especially in the spring. And these can be particularly onerous to predict and to forecast. So zoom in of a snow pit profile with dry on wet faceting would look like this. So you can see on this axis here we have our hardness scale, we have our temperature profile here, and then what we see in terms of depth is a very thin but very hard layer right here at about 205 centimeters. And then we have this extreme decrease in the hardness. So we have very fluffy types here. And if you look at the snow forms, here we have a melt freeze form followed by facets that are around 2.5 millimeters on average. And so we can see here from their test, this was the fail layer. And so the stratigraphy looks exactly like what we had discussed, where we have wet snow forms a nice hard bed layer, and then you have this less dense faceted layer. This is where the volumetric collapse occurs when you have more dense layers on top, and then you have some sort of pressure loading on the surface. So this is a pretty dangerous upside down portion of this. Okay, so a second type that we can talk about, which doesn't have a lot of literature discussion, but we'll talk about it because it really is a distinct type or distinct observation that you can find in the snowpack, is this one called strong gradient across a frozen melt layer. So again, starting with our initial cold snowpack, what happens is we generate some surface melt layer from warm weather or sun or whatever, and then that freezes on the surface as a crust at about 0 degrees C initially. But instead of new cold snow coming in, which is what we had for dry on wet faceting, we don't have any new precipitation. We just have a cold front that moves through, and so we get new cold air that's sub-zero, and that creates a strong temperature gradient across that crust layer, and the crust layer itself starts to turn into faceted forms. And so we sort of have a simplified time profile with various temperatures measured. So we have the surface temperature in green here, we have the air temperature in blue, and then you can see the established temperature gradient in the snowpack, with the onset of the cold front essentially being time 0 here. And so what we get is a fairly large temperature gradient that gets generated across the crust layer, typically a thicker crust. And as the cold front comes in, everything gets colder at the surface, and you can see that at roughly day 3 here, that's when we peak in terms of the temperature gradient across that. And then from observations, folks have seen facets start to form. So these melt forms actually turn into faceted forms around day 3, day 4. And then you can see up here in the second plot, this green line, that's the melt layer thickness. And you can see that thickness starts to increase as these facets grow. And they produce these sort of faceted melt forms that look like this under a loop. And these are particularly weak bonding to overlying snow, and so again you end up with these sort of persistent grain types that have poor bonding and decreases the overall stability of the snowpack, especially when you have a slab layer that is deposited on top of these. The third type is actually a pretty fascinating one, where you have facets that form below a melt layer or crust. So that means you have facets that are directly under the layer rather than on top of it, which was the dry on wet facets that we talked about before. And so here's a profile or cross-section of a layer that's been illuminated in a way that you can actually see these facets, a lower density facet layer that's actually sandwiched or laminated between two brighter melt crusts in the snowpack. And this phenomenon has been discussed extensively, actually, over the last several decades. It's been observed a lot, but the exact origin has been discussed and was sort of postulated maybe 20 years ago what the actual source or cause of this was. And it's been, maybe 5 or 6 years ago, this is 2016, where this has been experimentally validated. And so what happens is this ice layer, this crust layer, is so dense that it serves essentially as a cap. There's a couple phenomena that occur here that are important. One, that once you have this crust layer, it's important to remember that temperature gradients are really important, but really temperature gradients are proxies for vapor pressure gradients, right? Because the temperature itself is what dictates what the saturation vapor pressure is at any given point in space based on the Clausius-Clapeyron equation. And so when we have this crust layer here, some people call this an ice lens, essentially serves to trap water vapor. It's not as permeable to water vapor, and so it's not fair to assume this is necessarily a nice linear vapor pressure gradient across the lens itself or the crust itself. And so what you measure often experimentally is this blue line. So this is the temperature profile, the black lines here being the actual ice lens. And so you get this linear temperature gradient, which doesn't fully explain a driving force large enough for facets to form, honestly. And so, but what experimentally has been shown more recently is that if you put tiny little thermocouple probes that are sub-millimeter on either side of this crust layer, what you see are actually pretty steep gradients that form, which was predicted 15 or 20 years ago, but is only now shown to be proven. And so what you have is essentially the effect of differential vapor pressure gradients because of permeability differences in the crust and the snow and the layers on top. But you also have differential thermal conductivity, because when you have snow, you have ice grains, but largely you have a bunch of empty airspace. Thermal conductivity is very different in air than it is in ice. Here you have a thick ice layer, which conducts heat much faster than air does, and that allows you to create these very steep gradients, which are very thin, sub-millimeter, but even in sub-millimeter thermal gradient spaces, you can drive kinetic metamorphism of the snow layers that are adjacent to the crust. And that allows you to form facets on the underside of the crust layer. So the thickness of this crust and its distribution over a particular slope are really important for exactly the overall magnitude of these temperature gradients, and really whether or not facets will form at all, since this is a really thin layer. And that was demonstrated in this study, it's 15 or 20 years old now, where the folks did a variety of Roosh-Block stability tests on the same slope, but the slope sort of bridged from northeast to east, and it had a variety of sort of vegetative interference where the exact sun hit was not uniform over the entire slope. And so the lower scores here, these are the actual Roosh-Block scores, are on the sunnier left side of this convex roll, where the crusts and facets were able to develop on the shadier side. So you end up having differential stability over a slope that looks nominally identical, at least to a first-person observer. So it's really important to know the sort of finickiness and the nuance of faceting in adjacent melt layers. Okay, so the last one I want to mention is this radiation recrystallization or radiation crystallization, which is typically the motivating force for the Korn cycle. And so really this all comes down or comes from the wavelength dependence of the optical property of snow. And what I mean by that is captured in this figure over here, which is measuring the absorption coefficient, sometimes called the extinction coefficient, as a function of wavelength. And what all that's showing is that in ice and snow, you get a lot more absorbance of that or you have a lot less absorbance of that light in the snow at sort of bluer wavelengths, so closer to the UV out here. But as you move towards redder wavelengths out here, you end up with quite a bit more attenuation of that original light. And so this is almost all considered shortwave radiation from the sun. And then as we move further and further red, we end up moving into the infrared. And the long-wave infrared is the stuff that is re-emitted from black-body radiators. And so what's that really telling us is that shortwave radiation can penetrate deeper into the snowpack because it has a smaller extinction coefficient, and long-wave IR, the actual thermal part of the radiation spectrum, has a very, very high attenuation, so it doesn't penetrate very deeply into the snowpack, or it's absorbed by very thin layers of snow. So in the spring, when we have these really large diurnal solar flux conditions, meaning you have long, intense days, especially on sunnier aspects, where you can really get a lot of shortwave radiation, in the day, you end up getting this sort of warm band at the top of your snowpack. And that's because of the incoming shortwave. And remember, the attenuation of shortwave radiation is typically, 90-ish% is absorbed in that first 10 centimeters, depending on the albedo of the snowpack and the age and a variety of things. But it typically penetrates in a fairly macroscopic distance, 10 centimeters or so. But because of that same extinction coefficient, when that snowpack is heated up and it starts to emit infrared radiation proportional to its temperature, it attenuates it over a much thinner distance, which means all of the snowpack is actually radiating, but only this top layer allows the actual photons of light, those infrared photons, to escape the surface of the snowpack and actually effectively cool the surface. And so you end up having these differential components of heating and cooling from the sun. So you get deeper penetration and warming during the day, and then you get really shallow cooling events because of the long wave emission. So what happens is during the day you get quite a bit of liquid water generated because you start to melt that surface layer, and then as the system cools overnight, you end up refreezing those grains into clusters, and each cycle makes larger grains. We talked about that in wet snow metamorphism, so if you need a refresher on that, the driving forces for grains in cluster and sintering, you can look back at that video. And typically this occurs best in low water content, and you end up with clusters that look like this. These are sort of perfect corn clusters under a loop. When you have lots of water, meaning it's prolonged exposure to the sun and really sunny aspects late in the season, then you have so much water that you generate slush, and then the refreeze can be tricky because you can end up with sort of surface crust layers rather than these loose bonded structures that give you that good corn snow. Okay, so I want to leave you with a couple questions as you finish this up. I want you to think about some of the impacts, at least on the radiation recrystallization cycle. In this process where you have incoming shortwave light and outgoing longwave light, and it's really the balance of these systems, that melt freeze cycle, that generates these corn crystals. What happens when you have a windy day? How does that impact this cycle? How does it impact these phenomena? What happens if you have clouds overnight? So that's during the long wave emission step. What happens when you have clouds during the day? So that's affecting more the incoming shortwave. What happens when the grain shape and size get larger, so later season, older snow? And what happens when you have vegetation or trees that are adjacent to the section that you're evaluating or studying? So think about all those things on the impacts of these physical processes and see if you can come up